How does statistical mechanics explain macroscopic observations? Imagine trying to understand why a glass of water feels cold or why a hot cup of coffee cools down over time. These everyday experiences are tied to the tiny particles making up the water and coffee. But how do we connect these microscopic details to what we see and feel? That's where statistical mechanics comes in. It helps us see how the behavior of countless tiny particles leads to the large-scale properties we observe, like temperature, pressure, and entropy. At the microscopic level, a system is made up of a huge number of particles. Each particle has its own position and speed, moving in random ways. Every different arrangement of these particles is called a microstate. Because there are so many particles, tracking each one individually is impossible. Instead, statistical mechanics looks at all possible microstates and how likely each one is. Now, macrostates are what we measure, things like temperature, pressure, and volume. Many microstates can produce the same macrostate. For example, a gas in a container can have countless arrangements of molecules, but the overall pressure and temperature stay the same. Statistical mechanics uses the idea that the macrostate we see is actually an average over all these microstates. Entropy is a key idea here. It measures how many microstates correspond to a particular macrostate. The more microstates available, the higher the entropy. Think of entropy as a count of how many ways the particles can be arranged without changing the overall appearance. When a system has high entropy, it means there are many microstates, and the system is more likely to be found in that state. This explains why systems tend to move toward states with the highest entropy. For example, when you open a perfume bottle, the scent molecules spread out to fill the room. The molecules move randomly, and the state with the most microstates is the one where the scent is evenly distributed. The system naturally evolves toward this state because it is the most probable. Statistical mechanics also uses probability to describe how particles are likely to be arranged or how they move. Instead of knowing exactly where each particle is, we use probability distributions. These tell us the chance of finding particles in certain places or moving at certain speeds, which helps predict the overall behavior of the system. This approach helps us understand many phenomena. For example, when ice melts into water, the particles go from an ordered structure to a more disordered one, increasing entropy. Chemical reactions and heat flow can also be explained by looking at how particles rearrange and how their microstates change. In essence, statistical mechanics makes the connection between tiny particles and large-scale properties clear. It shows that the properties we measure are just averages over countless microscopic configurations. By understanding the probabilities and the number of microstates, we can see why systems behave the way they do, why they tend to move toward higher entropy states, and how spontaneous changes happen in nature.